Okay, hello everyone and welcome to our October WMESA seminar. My name is Melanie Finch and I convene the WMESA seminar series. WMESA acknowledges the traditional custodians of country and their connections to land, sea and community. We pay our respects to their elders past and present. While I'm in Australia, we're an international organisation, so I take this opportunity to acknowledge Maori as Tanata, Whenua and Treaty of Waitangi partners in Aotearoa, New Zealand. The WMESA seminar series is about showcasing the amazing work of women in earth and environmental science in Australasia. As well as the live seminars, we also have collated recordings from seminars that are hosted by other organisations. And we've put those up on our website and our YouTube channel, so you can go have a look at those anytime. So you can sign up as a member of WMESA for free to get a notification of upcoming seminars, or you can follow us on Twitter. Today's seminar is going to be presented by Dr. Katelyn Johnson, who is a paleoclimate scientist at GNS Science in Lower Hutt, New Zealand. Her research primarily focuses on reconstructing past climates from ice and marine sediment core records using a variety of methods. Her recent work has focused extensively on Holocene variability in the Adélie Land and Ross Sea regions in Antarctica. And she's currently working on multi-proxy reconstructions to better understand sub to multi-decadal variability across these regions. Okay, so without further ado, I'll hand over to you, Katelyn.
Okay. Share. Kia ora koutou, everyone. Thanks for joining and thanks, Melanie, for the awesome introduction. So today, sorry, I'm just going to work on moving people's faces for a minute. Get that sorted. See if I can put you on top. There we go. Thanks for your patience. So today I'm super excited to talk to you guys about a recent paper that I just had published in September, looking at reconstructing Holocene climate variability offshore Adélie Land, East Antarctica using a high resolution sediment core. The main focus of today's talk will be the study that was recently published, but I will start with just a brief overview of how I got to where I've been. I always find that fascinating when I hear how everybody's different paths, whether they're straight, circular, multiple loops, just to see how we all ended up here studying this incredible planet. After that, I will do a brief overview of the Southern Ocean and Antarctica, because I recognize not everybody studies Antarctica or is interested in paleoclimate, so hopefully that provides a bit of context for the details of the paper. And then I'll go into a bit of the future work that I'm working on as of now. So this work was, the study that I'm publishing, or that I published, is kind of the culmination of my PhD. And throughout that, I would like to thank all of my collaborators, as well as the organizations listed below. Science is never done in isolation. Thinking climate oscillations. It's never done in isolation, and it really takes a village and many teams, international teams, multiple time zones to get these things out into the open for everyone. And I'd also really like to extend my sincere thanks to WMESA for providing me this opportunity to present this research. So without further ado, I'll go into how did I end up studying past climates. So you can probably tell from my accent that I grew up in the Midwest of the US, so a place that's incredibly flat. There's no mountains, there's no glaciers, there's no ocean, there's a big lake, but what it lacks in topography, it makes up for in severe weather. So I grew up being fascinated by severe weather and thunderstorms. Anytime there was a severe thunderstorm, I was outside in it, which is probably not the best, but the power of nature really interested me, and I decided to study atmospheric science at Texas A&M. Texas A&M has an incredibly strong atmospheric chemistry department, and so I had been interested in climate science, and aerosol chemistry was a way to get involved. And so I spent some time setting up sensors around the greater Houston region, looking at biogenic aerosols and also aerosols and how they affect cloud formation. But during my time at A&M, I got to take several classes in climate and paleoclimate, and that's when I was introduced to paleoclimate research, and I decided that studying the past was more interesting than studying the present. And I moved to Ohio State to pursue my master's with Dr. Lonnie Thompson, looking at El Nino Southern Oscillation signatures in tropical ice auroras. As a part of that, I got to participate in some field work at Calcaya Icecap in the Peruvian Andes, which was an awesome, awesome experience. After my master's, I decided to take some time off. I wasn't sure if I wanted to stay in research. And as most young Earth scientists at the time, I ended up in oil and gas, which was quite a surprise for me. It was not a place I ever expected to be, but I learned some incredibly valuable lessons. As part of that, there are a couple of different aspects in oil and gas that I participated in. One was met-ocean investigations, and so that's studying the meteorological and oceanographic conditions that you need to design a structure to or plan for when you're installing a structure. So that worked, spent a lot of time working between project managers and our research group looking at hindcast models and also preparing those design criteria. I also spent some time developing reservoir models for the Gulf of Mexico and was fortunate enough to be able to spend some time on a deep water drill ship drilling in the Gulf of Mexico, which was just a really great experience. But in 2016, I decided I was done with all of that and wanted to get back into climate. And so my partner and I moved to New Zealand to pursue our PhDs. There was a project available that enabled me to work not only on ice cores, but sediment cores. So that was cool to really combine two of my passions and work experience. And that picture on the far right is my first time ever seeing an iceberg on the RV Aeron on a Korean icebreaker for a cruise in the Bellinghausen Sea. That just really had a huge impact on me, and everybody makes fun of me because of my hands. I don't know what I'm doing with my hands, but I was just really excited. And since then, I've just decided to stay in research. I finished my PhD in 2020 and have been at GNS ever since. So to move on and get into the nitty gritty of Antarctic and Southern Ocean, that's quite a big title for just one slide. So I wanted to start with a very broad overview because I know not everybody is interested or studies Antarctica, but provide some broader context of why the paleoclimate studies in this region are particularly important. I would argue paleoclimate reconstructions are important all over the world, but in Antarctica, we're even more limited in terms of temporal and spatial records. And so paleoclimate records help us reconstruct the past environment so that we can better contextualize how climate change will impact this region in the future and how it has reacted to different climatic conditions in the past. And in terms of Antarctica and the Southern Ocean, it's far away. I mean, it's close for most of us in Australia and New Zealand right now, but it really has a global impact throughout the world. So I really like this simplified schematic from Meredith et al. In 2013 that shows the complex ice-ocean atmospheric interactions in the Southern Ocean. And the two key things I want to highlight for this presentation is sea ice and phytoplankton. They do not act in isolation, but it's really important that we have good paleoclimate reconstructions for them. So sea ice impacts many things in the Southern Ocean, and it plays a variety of roles. But one of the impacts is that it helps, the formation of sea ice helps forms of precursor water masses through brine rejection. So as sea ice forms, it rejects all the salt, and that forms a dense salty water mass that sinks, joins with other intermediate water masses, gets exported off Antarctica's continental shelves, and helps drive Southern Ocean overturning circulation. But from another impact, sea ice also can impact carbon dioxide fluxes, and sea ice, particularly in the winter, it majorly impacts the air sea ice flux and acts as a cap to kind of keep carbon dioxide from upwelling during the winter, or keeps it from releasing into the atmosphere, I should say. So when we think about these impacts, not only for global ocean circulation, but also carbon dioxide and the carbon cycle. So the world's oceans have taken up between 1/4 to 30% of anthropogenic CO2. And the Southern Ocean has taken up about 40% of that. So it's a major carbon sink. Now, While sea ice plays a key physical role in that, at least in the winter, it doesn't have a huge impact in terms of keeping things sequestered once it melts. It also acts as a substrate for phytoplankton, which is incredibly important for the carbon uptake, because the biological pump sorry about that. I knew I was going to get a phone call during this presentation. Let me ignore that. Thank you. So where was I? Sea ice and its role for biological productivity. So the biological pump, so in the 40% that the Southern Ocean uptakes, about 10% of that uptake is consumed just by the biological pump. So we get these massive phytoplankton blooms. They uptake CO2. If they die, they sink, they get sequestered in the Southern Ocean. So for sea ice, it can act as a biological substrate. So ice algae can live at the bottom of sea ice, but also it provides, it affects nutrient delivery, water stratification, and solar insolation, which all controls these phytoplankton bloom events. And so they really act in sync, and it's difficult to study these in terms of past in isolation. You really need to look at both your sea ice and your biological productivity to try and get a bigger picture. And by looking at these two in particular, you can understand a larger part of the global climate cycle and completion. So I'm going to jump to the next slide, which is Antarctic sea ice. And as I mentioned, that winter sea ice extent can be quite important. Sea ice extent over winter in Antarctica nearly doubles Antarctica's size. So if you're looking on your left, you're looking at the winter maximum, and that's for 2020. So the winter maximum in Antarctica is typically reached in September, and then you have kind of the median measurement from 1981 to 2010, the median extent. Now, in the summer, the sea ice retreats over several months. And so this is February, where it's reaching its minimum extent. You can see we still have a bit of sea ice hanging around the fringe. And it's important to highlight that a lot of this is fast ice. So that fast ice is because it's literally fastened to the Antarctic continent along the coastal margins. And so that's important for key studies. So I just wanted to point that out. But there's an Antarctic sea ice paradox in that we've known for the Arctic sea ice has been decreasing for quite some time, but up until 2015, 2016, Antarctic sea ice extent was actually increasing, and we weren't quite sure what was going on there. At that time, there was a massive decrease, and I believe it was 2016 that it reached a minimum, but it's slowly been recovering since then. And how sea ice changes is going to affect primary productivity and several other processes. And so creating long-term sea ice records is really important for understanding these changes and contextualizing current events. So as I mentioned, the Antarctic sea ice extent is very important for primary productivity. This is a graph from Depler and Davidson in 2017, which is looking at primary productivity in the Southern Ocean, looking at chlorophyll measurements from satellites. So if you look at this pink circle right here, that is the maximum winter sea ice extent. So I just want to note that, because the seasonal southward retreat from your maximum sea ice extent in September all the way to your minimum in February really initiates phytoplankton blooms, because it provides nutrients, it stabilizes the melt water layer and in freshwater fluxes. And so the changing of the timing of sea ice growth is really important, because it will alter the timing of these blooms. Well, the largest productivity in CO2 sink is typically around this area where we have the front of the Antarctic circumpolar current. We also have very high levels of primary productivity along the Antarctic continental shelves. So if you look at this, it's quite hard to see, but this little light blue line, that's the 1,000-meter isobath on Antarctica's continental shelves. And despite their very small size, they're highly productive. A study by Arrigo in 2008 estimated that CO2 uptake in the Ross Sea was responsible for about 27% of the total Southern Ocean CO2 uptake. The high productivity region along Antarctica's continental margins is due to high surface nutrient concentrations. The Southern Ocean is typically iron limited, But in this region, we can get iron from upwelling of upper circumpolar deep water. We can also get iron input from basal shelf melt and coastal sediments. And we also have the fast ice, which acts as really helps polynyas along the coastal margins, which we'll talk about in a second. So if we were to take that previous graph and turn it into a 3D model, this is what it would look like. We have the Antarctic circumpolar current all the way out here, moving in towards the coast to where we have polynyas. And so this is where we're going to focus most of the study on. So polynya is an area of open water or reduced sea ice cover, located in waters that you would expect to be ice covered. And the way polynyas form is you have strong katabatic winds flowing from the high plateaus of the Antarctic ice sheet down off the coast. And as that you get these cold winds draining from the ice sheet, they push sea ice away from the coastal area. And as you do that, you expose more open water, but you continuously have these cold winds flowing over it. And when that helps form more sea ice. And so these polynyas become mini sea ice factories. They're constantly producing sea ice, they're constantly pushing it away. And you can just kind of, polynyas are some responsible for quite a bit of the sea ice production around Antarctica. Now, this sea ice production is incredibly important because, as I mentioned, as sea ice forms, you get this brine rejection, this rejection of salt. And so you get these dense, salty water masses forming that sink, interact with different water masses, and then form Antarctic bottom water, which gets expedited in the abyss to help drive global overturning circulation. In addition to being sea ice factories and producing all these precursor water masses for dense water formation, we get the surface waters in polynyas are associated with high biological productivity. And this is typically because they are the first in the marine systems to be exposed to increasing radiation in the springtime, either because they lack ice cover altogether or the ice cover that is there is weak and easily able to break out and melt in the spring. The average phytoplankton concentration in polynyas tends to be about more than double than what you would have in an open ocean region. And so studying these polynyas is incredibly important for creating these long-term records of biological productivity in sea ice. And this is just an example of bloom events occurring around the continental margin, just for near the Ross Sea. You can kind of see the green sludge. It's more evident around the Terra Nova Bay polynya and the Drygalski ice tongue, and also in the Mertz polynya. It's very difficult to have measurements directly in polynyas. You need a icebreaker to be there, and you need for it to happen at just the right time. You typically have a narrow window for these to occur in springtime, and so measurements are incredibly difficult to get. It's also not enough to just go to one polynya and think that you understand how it's behaving. Each polynya is different and they have different characteristics, and they're not spatially coherent. But studying a key few, such as the Mertz polynya and the polynyas along the Adélie coast, are important because this area is responsible for up to 25% of Antarctic bottom water formation. It's one of the most productive in terms of sea ice, I think in the top 4. And so this kind of sets the stage for why this area was incredibly important. It had been noted by quite a bit that the coastal region in Adélie Land was a site of intense and frequent diatom blooms, and they are transported large amounts to depth. And if you have an area of high sedimentation, you can potentially get a record that can be used to reconstruct not only the bloom events, but look at sea ice through time and really help bolster these records and better understand this system. And this leads me to the study that was just published in September. And this is a culmination of quite a long time. This study was first submitted in October of 2019. So I'm very happy to finally see this thing out and show you all the excellent work that was done on this record. So going back into the study location, I've highlighted why the Mertz polynya is quite important, and records around the Mertz region and Adélie Land region are quite important. So down here to the graph is just a schematic of showing some satellite images of the core site that we're interested in, indicated by the orange dot. where we have sea ice breakout, and about a month later where we have these phytoplankton blooms occurring. So going to our map, this is the bathymetric profile. So this data used to make this map is from Beeman et al. In 2010, where they were able to create a higher bathymetric model for this area. But in 2010, 180-meter laminated sediment core was drilled as part of Expedition 318 as part of International Ocean Discovery Program, IODP. This record has one of the highest sedimentation rates in the world. It's about 1.5 centimeters to 2 centimeters per year. And the reason for this high sedimentation rate is because of the high biological productivity. So directly over this site or nearby is the Dumont-D'Urville polynya, but we also have the Mertz polynya to the east. Because of the wide shelf, we also have quite a strong coastal current, and that's in part wind driven due to these strong katabatic winds draining off the coast that then get turned by the Coriolis effect into zonal winds, which helps drive this zonal coastal current. So all this biological material, you get these big blooms, they die, they rapidly sink, they're transported by the coastal current and then deposited into this basin. To the left, we can see the seismic profile taken of this drift deposit. And you can actually see the alternating light and dark scale laminations in this record. To our knowledge, there's one other continuously laminated sediment record, which is about 2,000 years long, done by Karen Alley. So this record goes back about 11,400 years, which is really exciting to see what we can pull from it. So when I talk about a laminated sediment, this is what I'm actually looking at. This is about 15 centimeters of core section, where you see these nice alternating light and dark scale laminations. Now, diatom analysis from nearby cores within this drift deposit show that light laminations correspond to multi-year bloom events during the sea ice retreat or regrowth phase, whereas dark laminations will correspond to open ocean conditions. Now, we really want to be able to quantify these light laminations to better understand how frequently these bloom events due to sea ice retreat or regrowth occur. And in order to do that, we decided to CT scan the entire core. This is when my life kind of went full circle, because I don't think I had been in New Zealand for more than 5 months when I flew back to Texas to go to Texas A&M to CT scan these cores in the petroleum engineering department. It was quite an interesting time for me, but we CT scanned these core sections in sets of 12 just for time efficiency. That left us separating these cores out in post-image processing. But through that, we were able to pull out core profiles. So on the left, this is line scan photographs. So initially, counting of laminae were done on these line scanned photographs, but there was differential oxidation that occurred when the core was exposed. And so that limited everything that you could see just by eyesight. And so you can see the difference that CT scanning the core makes. Now, to develop our paleoclimate record, we took made a grayscale curve from that. And so what that means, that's measuring the variation from light to dark in the core, which is a measure of density, to really highlight changes between light and dark laminations. So these light yellow, these yellow layers are light laminae, and those are going to produce really high pixel values because they're super bright, whereas our dark laminae are the blues and greens, and those are going to have really low pixel values. Yeah, they're just going to have low pixel values. So typically in a CT scan, when you're creating a grayscale profile, you would take the entire core width. But as you can see, these cores had been U-channeled for another process before we CT scanned them, because we CT scanned them about 6 years after they were drilled. And so I just took a line profile along one side of the core to produce this record. In conjunction with that, I also went through and manually picked all the different laminae and all the light laminae and the tops and bottoms of that, so we could have laminae thickness. And I overlaid those light laminae onto that grayscale profile, and those are seen just by those orange dots here. One of our collaborators had also performed X-ray fluorescent measurements at 5 centimeter intervals. And it's just important to highlight that even though this is a lower resolution record, just because of what it was measured, the sub-millimeter resolution record of the grayscale profile really aligns well to the XRF data, indicating that the grayscale profile is able to capture changes in sedimentology. So from this, we were able to count the number of laminae, but also create a frequency record. And so we binned the record into 10-year intervals to better understand how many laminae events were occurring per 10 years from about 11,400 years to present. And in order to produce this curve, we of course need an age model. So I just wanted to quickly show you all this. So our age model is constrained by 84 bulk organic carbon ages. That's shown in blue. We also have compound-specific ages from the adjacent core U1357A, and that's in green. So for those of you that don't know, IODP tends to triple core a site. That's just in the case of incomplete recovery. You can be able to splice a core together to create a composite. But it's really great that these two aligned, two different age dating methods. But then the third one is that there's a comparison with nearby Mary and Dufresne core, which is just downstream in the same Adélie Basin, but shows that the sedimentation really reflects a regional pattern. U1357B is just not one-off. This is going on in the basin as a whole. And so to better understand kind of the paleoclimate environment, we created a simplified deposition model to explain what was going on in this region. So there's a distinct lack of perglacial flans in the region. And so that's just a lack of meltwater plumes. We also have grain size data from the banks as well as in the basin. And so what we know about this region, there's Kate Snow did an incredible study in 2016 looking at summertime circulation, which did show that this region is strongly affected by an Antarctic coastal current, which makes sense just because of the strong katabatic winds, but also the easterly winds in this region. But the grain size data suggests that when you have, if you can imagine that up here, you have your little Mertz polynya, and then over here, you probably have your Dumont-D'Urville polynya. When you have these big bloom events, they kind of run out of nutrients, they sink and die. They're going to be transported by the Antarctic coastal current. And then as that current flows over the basin, that's going to cause a slowdown. And so you're going to get a selective deposition of material. We also know we have a slight terrigenous component from winnowed sediment from banks, because the distinct grain size profile that we see in the basin is the same grain size profile that's lacking along the banks, suggesting that it has been winnowed over time. And so if we're thinking just from a climate environment, if we have more coastal sea ice, that's going to prevent the strength of the easterly winds from really having an effect on the surface and translating via depth and pumping. And so if you have more coastal sea ice and perhaps weaker winds, you would expect to see in your record reduced grain size, reduced mass accumulation rates, and reduced laminae thickness. Whereas if you're in an area with less coastal sea ice, you can have more energy on the ocean surface from stronger winds, and you would tend to see a bigger grain size, bigger mass accumulation rates, and increased laminae thickness. So what does that look like over the entire Holocene? So this is the Holocene reconstructed by U1357B. So up top, we have our mass accumulation rates, which is a proxy for our sediment advection. We have that divided both in biogenic as well as terrigenous. We have that laminae frequency through time. So it's counting our biogenic bloom events. That's the frequency record I showed you on the CT slide for the image analysis. We have a current speed proxy that's derived by taking the sand percent of the light laminae, so the sand percent within these light bloom events. And we also have two great sea ice proxies. One is the IPSO-25, an HVI biomarker proxy measured by Johan Eterno throughout U1357B. And then we also have the Fragilariopsis curta data from Xavier Costa from the Mary and Dufresne core, which is downstream. And so there's two key things. We have sediment advection rates, the laminae frequency and current speed all covary, indicating that sediment advection at the site is really driven by current strength. And we also notice the distinct effect that sea ice has on the region. So we have this massive increase in sea ice around 4,500. And as we have this increase in sea ice, we notice a drastic reduction in current, but also bloom frequency. So up until this time, we have bloom frequency, phytoplankton bloom events occurring every 1 to 2 years during periods of reduced sea ice. As soon as we enter a period of increased sea ice, this switches to about a 2 to 5 to a 2 to 7 year frequency, which is curious. It's curious because that frequency tends to correspond to subdecadal climate oscillations. And so in order to see, pull out other frequencies in a more statistically significant way, other than just binning the data, we took the grayscale profile, so that big high resolution black curve that I had showed you on the CT scan slide, and we did evolutive harmonic analysis on it. And so that's shown in this panel on the left, and on the right, we did the same study for, or the same process for the XRF data, but this time we used a silica titanium ratio, which is used in paleoclimate studies as a paleoproductivity proxy. So we did the evolutive harmonic analysis on that, and then we overlaid our laminae frequency, the bin data. And it's pretty great that we get good agreement across both proxies and multiple different methods. And so you can see in the middle Holocene in particular, we have quite frequent bloom events occurring every year. In some cases, particularly around 8.2, they're occurring more frequently than every year. And then once we hit that 4.5 interval, we see that big reduction, and where most of the frequencies are occurring in subdecadal climate modes, or the ENSO band. We know in other studies that primary productivity, particularly in the peninsula, is affected by climate oscillations, and this is through sea ice and winds. And this makes sense because in order for these bloom events to happen, the wind conditions have to be just right, and we also need sea ice to break out and melt to kind of induce these bloom events. What's interesting is that when we have a change in sea ice state, that relationship between climate oscillations and what's the dominating factor changes. And so to kind of unravel this, we need to understand what's going on in the modern day environment. Now, I have this listed as the modern day environment. This is really pre-2010. And this is an excellent figure from Maslam and Stammerjohn in 2010, which looks at the icescape in the Adélie Land region. So just over here is the approximate location of where we would have U1357b. And Maslam and Stammerjohn have done a great job of labeling the different aspects of the icescapes. So this is pre-2010 because the Mertz Glacier tongue broke off in 2010, so you would be missing this area. But in coastal Polonia, such as the Mertz Glacier, this presence of glacial ice actually deflects vast pack ice and vast thick flows of sea ice away. And so you have fast ice to the east and also fast ice to the west, and the glacier tongue sticking out and kind of deflecting all this stuff that's being transported around the continent. Now, what that allows, it allows for the Polonia to stay open, for you to continue to produce sea ice and also to have primary productivity. However, when you have this fast ice over here to the left, if you have a change where you have an increase in sea ice and a change in the winds, you can actually backfill the Polonia. So you can actually restrict the export zone for the Polonia for where it's unable to export any sea ice. And so what that will do will kind of restrict, you won't have any open water, and you will severely limit the primary productivity that you do have, and you will limit the amount of sea ice you can produce, because you can't produce more and more sea ice on top of sea ice. It has to be transported out before you can produce more. So if we're thinking back to our proxies in around 4,500 years ago, when we have this huge increase in sea ice, it's not hard to imagine that if you have this increase in sea ice over the over U1357b, these backfill events were likely to occur more frequently, or you just weren't having any open ocean environments altogether for several years. The fast ice was just too thick, it wasn't breaking out, it was really hard to kind of break it up to induce these bloom events. So the theory we have is that once you have this increase in sea ice state in general, it becomes really hard to break out that sea ice. But perhaps there's some alteration in the climate state from these subdecadal climate modes that might increase the threshold, change the climate enough that you can break out these sea ice at subdecadal frequencies, such as, say, you have an ENSO event and temperatures are warmer and you have reduced sea ice. That may be enough to induce a bloom event that you wouldn't get in a normal year without those climate anomalies caused by things such as ENSO. Now, a study by Lee et al. In 2021 highlighted that the expectation, based on what we know now, that we would have warmer surface air temperatures and reduced sea ice in this region. But understanding the direct mechanism of what climate mode is actually creating this impact, what phase it's in, is very difficult. So there's limited studies in East Antarctica, and actually in Lee et al., this Nature Review paper by Lee et al. Highlights that East Antarctica is an area that is significantly understudied. Most of the knowledge we have about climate oscillations, particularly their impact on primary productivity, is on the peninsula and also in the Ross Sea region. We also have multiple climate modes affecting this region and multiple types. So El Nino has two different types. There's a Central Pacific type, which is probably more likely to impact the Adélie Land region, or the more commonly known Eastern Pacific type. We also know that when El Nino is in phase with something such as the Indian Ocean dipole, that can have the opposite effect, where you have increased sea ice and cold air flows, and that would have the opposite of impact of what we're seeing here. We also have the added complication of SAM, which the southern annular mode, which acts to either enhance or reduce the teleconnection strength of El Nino. And then we're dealing with a even larger problem, which is the seasonality of these impacts. And so I mentioned that the timing of sea ice and retreat is very important for how these bloom events occur. And so these climate teleconnections are actually stronger in certain seasons over others. And so while this is an incredible record with near annual resolution, being able to understand what's happening seasonally is difficult as well. We're also limited by paleoclimate records with the southern annular mode and Indian Ocean dipole are incredibly lacking. There's been a lot of great research coming out in the last several years where they've reconstructed these things over the last 1,000 years, but it's going to take a bit more time, a few more studies before we're able to say with any great certainty what the direct impact is going on here to cause these bloom events to occur at subdecadal frequency. So in summary, for the paper, I just want to say U1357b provides a near annual record of phytoplankton bloom events, light laminae, from about 11,380 years present. This is probably the highest Antarctic sediment core record and longest for the Holocene. It has resolution that's equivalent to an ice core, which is incredibly exciting for multi-proxy reconstructions. Sediment advection at the site is largely driven by current strength, which is influenced by winds. The increase at sea ice at about 4,500 years before present corresponds to reduced bloom frequency and current strength. And the frequency of phytoplankton bloom events appear to be influenced by climate oscillations through its impacts on sea ice and winds. This is in agreement with other studies around Antarctica, but the background sea ice state is incredibly important, because when we don't have that increased background sea ice state, we tend to lose that really important imprint of those records. So with that, I'm just going to move quickly to just some studies that have been spurred on top of this, some additional analysis we're doing. Right now, I'm currently in the process of refining our current proxy that we presented and taking a second look at our grain size data. So Anya Albert, who's an incredibly talented master's student, had measured the grain size data in 2016. We have grain size data for both the light and dark laminae. And grain size data have been used in the past to infer paleocurrent strength, but this has typically been very difficult in ice proximal settings. And the general reasoning behind that is typically when you're using grain size as current strength, if you have larger grain sizes, that means you have a stronger current. However, in ice proximal settings, you can have sediment of larger grain sizes being transported by sea ice or icebergs. And if you have larger sediment not transported by the current, that's obviously going to affect your current proxy. But McCabe and Andrews came up with a new method in 2019 where they suggested if you ice-rafted debris was quite low, less than 50%, which is the case in our core where we only really have IRD in the last half meter or so, and you had a well sorted, it could be used as a current proxy. To determine if the proxy is well sorted, you compare the percentage of grain sizes in a certain range versus the mean grain size in the same range. They use proxy sortable silt, which is about 10 microns to 63 microns. But that's typically for deeper ocean environments. And we have something quite interesting where we have a bimodal distribution in the coastal continental shelf setting that we're in. And so we adapt the May Cave and Andrews method to be comparable for something on the continental shelf, and suggest that 36 to 125 micron mean size is a better indication of current strength in this region. So this is just looking at the light laminae. And on the left, this is just showing that 9-point running correlation that they had mentioned, where the proxy passes as one you can use for paleocurrent proxies. In areas of blue, that's where the sediment's not well sorted. In areas of yellow, you're well sorted enough. And so this on our right is our reimagined or refined light laminae current proxy setting. I also have this for the dark laminae, which is important. In the dark laminae, tends to show that we have increased current during dark laminae, which is important and interesting just because we expect open ocean conditions that fits in well. Then once we have this refined paleocurrent proxy, we then started looking at laminae thickness, which I have throughout the core. So this is laminae thickness detrended. This is just a linear detrend to make up for the core compaction. But we generally see that higher current speeds are related to increased laminae thickness, but we do know that laminae thickness is likely related to several factors. It's just not going to be related solely to wind strength. It's also going to be related in part to biological productivity. But variations in zonal winds may be reflected in laminae thickness, so we've done a bit of statistics on that as well. And notice we have quite a strong frequency in the 10 to 40 year band, which is maybe related to the interdecadal Pacific oscillation. Another area we're looking at is changing icescapes. So there was a study that came out 2017, perhaps, maybe a bit earlier, that looked at the Mertz Glacier tongue calving. So when I was talking about the sea icescape in the Massam and Stammer-John figure and how loss of the Mertz Glacier tongue affects this region, it's come out, several studies have shown that we have increased carbon uptake, and that's from increased productivity, but we have reduced export of Antarctic bottom water. But seeing if we can somehow tease out the frequency of the Mertz Glacier tongue cavity through this record and looking at the longer term cyclicity and trying to extend the previous work that's already been done in this region. Jansen et al. In 2018 gave this great figure that just shows the differences that they would expect in deposition from having the Mertz Glacier tongue versus not. So it'd be incredibly interesting to try and tease out those differences. And last but not least, I am an ice core scientist as well. And so I'm currently working on looking at Holocene change in the Ross Sea and Adélie Land regions and integrating this Adélie Land record with an ice core record, most specifically the Roosevelt Island Climate Evolution Project. The sediment core record, because it has near annual resolution, this is an exciting opportunity to integrate an ice core record with a sediment core record of equal resolution. And there's a lot of interesting stuff happening during this time, during the Holocene, particularly understanding the retreat of the Ross Ice Shelf. And so looking at multiple ice core records and sediment core records within this region can kind of create a more complete picture of what's going on regionally. Preliminary work on this has been completed, but the bigger challenge here is the age models. And I think many people who work on multi-proxy paleoclimate reconstructions can relate. It can be somewhat easy to get a record where you're looking at things on 200-year intervals, but if you're really trying to understand what's going on at subdecadal scale, you need to be able to refine the age models and align them in a way that minimizes the age model error. So with that, I will take any questions.
Thank you so much, Katelyn. That was such an interesting talk and overview of the work that you've been doing. If people have questions, they can pop them into the chat, or you can unmute yourself and turn your video on, and hopefully I'll see that, and then I'll just call on you, or you can just sing out if I don't. That's fine as well. The thing that really is, so I'm just going to ask a question while people are thinking about that. Yeah. And, you know, I'm aware that I'm a geologist, and so these questions might not be the best ones in the world. But that's what I was wondering when I was reading your paper, I think, and listening to your talk, it really struck me how many different variables affect these systems. And so, gosh, that just seems like a really difficult job to constrain what's going on. Yeah, it's incredible. And of course, like, you know, I have the question that probably everybody asks you, which is that, you know, Antarctica, the sea ice is increasing until, I think you said 2015, and then there was a massive decrease and now it's increasing again, whereas in the Arctic, I think it's just decreasing, correct me if I'm wrong. And so I was just wondering what sort of factors are in play around Antarctica that aren't in play in the Arctic that are causing sort of the response to climate change to be so different.
Yeah, so it's quite a multifaceted, and I'm by no means an expert in some of these sea ice dynamics. I think some of the impact is just the some of the climate oscillations and the certain phases that they're in. And some of these are not the subdecadal, it's the multidecadal. And so who knows, with things changing in the future, there's just quite a bit of flux, and I don't want to, so in part, some of this is southern annular mode. This is by no means the dominating factor. I mean, it's still quite a mystery for a lot, but southern annular mode has been in a positive phase recently, but that's in part due to the ozone hole. And since we're repairing the ozone hole, that might change. And so kind of deconvolving what's going on is quite challenging, which is why they suggest the sea ice paradox. And it makes it even more challenging because from satellite records, we have 40 years, 50 years of satellite records. And so understanding the long-term variability while also trying to understand the impact of these climate oscillations on that can be even more challenging because we just don't have the records to kind of compare it to.
Mm-hmm. Yeah, sure. I was also wondering, I mean, I was particularly, concerned, I guess, about how you had that picture from 2010 that had the Icescape and had the Mertz glacier in there, and that it then wasn't there anymore. And that made me wonder about Icescape changes in sort of the more distant past where we don't, I wondered whether there were huge changes like that really affect the way flow happens around Antarctica and affect sort of records like the record that you were looking at, and that we just don't have any records of the previous Icescape. Is that a factor that is particularly troubling in your field?
Yeah. I mean, I guess it can be. Thankfully for the Holocene, there are other onshore reconstructions of things we can expect. The ice tongue actually collapsed just because it collided with a big iceberg. So it wasn't, but when we have icebergs floating around the continent, it's always a thing that can be incredibly challenging to kind of visualize. But in that area, we know, I guess, from Antarctica, the East Antarctica was still deglaciating. So part of my hesitancy to look in kind of clearly define some of that early Holocene. So from about 8.2 to 11.3, we know that area or suggests that area was still deglaciating at that time. And so because of that, you're going to have a different situation. You're not going to have that strong coastal current. Actually, on those banks, you would still have glaciers, and it's kind of a calving bay environment. And so because of that, you can't draw the same conclusions as you can earlier in the record.
Mm-hmm. Sure. Cool. Great. And I was also, I'm just going to keep going. I've got a list of questions. So please, if anyone else does, please just sing out. Feel free to unmute yourself. That's totally fine. I was also wondering, well, I'll ask this one from Richard Jones in the chat. So he says, great science, Katelyn. Do you think that the change in sea ice extent at 4.5 thousand years ago is that right? Okay, yeah. I work in MA, so is related to a shift in the configuration or stability of the Mertz ice tongue?
Ooh, that's an excellent question. I'm not entirely sure. So I think a related study that came out of this due to some fatty acid work that looked at freshening of the water mass. We did some modeling. So this is Kate Ashley's paper in 2021, where there's a suggestion that the increase in sea ice extent in the Mertz region was actually due to the development of the Ross Ice Shelf cavity around this time. That the development of that altered surface water mass enough to kind of increase sea ice regionally. It's also been, the increases related to insulation changes as well. I'd be interested in, how the change in the Mertz Glacier tongue would kind of impact that, because if the Mertz tongue was growing in that region, it would actually block more sea ice to the east and leave more open ocean to the west. Sorry, I get my east and west. Antarctica is a nightmare. To the west where the site is, and so I would actually expect for it to be more open if there was more a larger tongue there at the time.
Cool. I was just wondering if...
Emily, it's Mike Hall. Can I ask a question?
Go for it, Mike.
I'll turn my video on so Katelyn can see me. Is there any correlation between the changes you've seen in Antarctica, for example, in New Zealand? I know it's a long way away, but I just wondered if you were seeing a larger climatic effect than just simply confined to Antarctica?
No, that we are actually that's one of the areas we're looking at, particularly when we see this frequency that we might be related to the interdecadal Pacific Oscillation. There are quite a few paleoclimate records in New Zealand that indicate that as well. So it would be really cool to have a transect from New Zealand all the way down. It's been incredibly impressive to see what folks in Australia have done between Law Dome and the rainfall and the droughts in Australia. So it would be keen to see a similar thing go on for Adélie in New Zealand.
Oh, thanks.
Cool. I was also wondering about the use of X-ray tomography. That's what you use, right? And so I was wondering, that seems like, and you went all the way to Texas to do it, and that seems like a really involved technique for pulling out those laminations. And when we could see those laminations, just by looking at the picture you had there. So I was wondering why such impressive detailed sort of technique is necessary. Is it the resolution?
Well, there was a few reasons. So some of the core faces, when they were exposed to the air, they oxidized, and so you had the colors actually changed, and so it was quite difficult to see some of the laminations. So that one picture that I showed where it was quite clear, that was taken directly when it was brought on board. So that was part of it. The other thing is there's a lot of biogenic gas in the core, and so this caused millimeter scale cracks throughout the core, and some of the image processing that's available with the CT scan just made it a bit easier to kind of, ignore that in terms of just kind of remove it as noise from the data set.
Yeah, absolutely. That makes a lot of sense. Yeah, you did mention that oxidized thing. I didn't, really, that's cool. Yeah, absolutely. Cool. Okay, well, we're almost at the hour. I say at the hour because who knows what the time zone is anymore with all the changes in daylight savings. So I'll draw it to a close. And if people think of questions later, you can always get in contact with Katelyn offline. But with that, I just want to thank you so much, Katelyn, for that brilliant seminar and introduction for me into this field of science. So it was really wonderful. Thanks so much.
Yeah, no, thanks everyone. I really appreciate everyone